Hello friends, welcome back to my channel. So if you are new to my channel, please do subscribe for more videos. So today our topic is VLSI testing. So in part 1 video I had already discussed the introduction, so fault models and test vector generation. If you don't see that particular video, so that particular link will be given in the description. You can go through that particular link. So okay, now in this particular session I am just going to discuss these two topics, fault simulation and design for testability. So all these topics I had already completed. So today our topic is the fault simulation. So before going to discuss the definition for the fault simulation, so let me tell you what is meant by the simulation actually. So simulation is the process of using a simulation software. So that is a simulator. So to verify the functional correctness of a digital design, so that is modeled using the HDL like VHDL or Verilog. So that means by using VHDL or Verilog languages, we can identify or we can verify the functionality of a design. Okay. So what is in simulation, there is no need of any hardware. So what is the advantage of doing simulation means, for suppose if you want to test the functionality of some design, if you directly purchase the hardware from the shop and connect all of them, so if there is a fault in the digital design or in this particular design, so what will happen if there is a fault? All your hardware will be gone off. So all your time, effort and cost is going to be waste. So that's why before going to use the hardware, so we have to simulate that particular design. So if that particular, if you simulate, so if the simulation will give the accurate result, if the simulation results are satisfactory, then only you can proceed with the hardware. So that is the advantage of doing simulation. Okay, simulation reduces the cost, simulation reduces the effort, simulation reduces the time of a manufacturing. Okay, so it is defined as process of measuring the. So now we can discuss fault simulation definition. Fault simulation means this is the process of measuring the quality of a test. It is performed using gate level model and functional level model. Okay. So see here, functions of fault simulations. So it will confirm the detection of the fault. So fault simulation means by doing fault simulation by some kind of a simulator, we can detect the faults in the particular design. So it can also compute the fault coverage. So here the fault coverage will be expressed in percentage. So which is expressed as number of faults, the ratio of number of faults detected to total nodes in the circuit. So it is nothing but fault coverage. It is expressed in percentage. So always remember, high fault coverage is desirable. Low fault coverage is not desirable. So mostly we can observe the high fault coverage in the digital design. Okay. So see here, what are the types of fault simulation? We have mainly two types of fault simulation. Those are deterministic fault simulation and non-deterministic fault simulation. In deterministic fault simulation, so let me tell you, so what are the differences between these two simulations? Deterministic fault simulation and non-deterministic fault simulation means, in deterministic fault simulation, we are going to test all the components in the design, all components. So in deterministic fault simulation, we are going to test each and every component in the digital design. So whereas in case of a non-deterministic fault simulation, we are going to test only some. We are going to select some samples. Only we are going to test some samples. Okay. So in deterministic, we are going to test all the components. Whereas in case of a non-deterministic, we are going to test some components in the digital design. Okay. In order to identify the faults. So in the deterministic fault simulation is divided into serial simulation, serial fault simulation, parallel fault simulation and concurrent fault simulation. So in the non-deterministic fault simulation, we don't have any classification. So let's see the serial fault simulation. In serial fault simulation, we are going to test or we are going to simulate one after another. Okay, this is somewhat slow. Why? Because this is simulated one after another. here we can use two copies of the circuits. The first copy is a good circuit and second copy is generated from the first copy only. By inserting a fault into the first copy, we can generate the second copy. So that means the first one is a good copy circuit and second one is a faulty circuit. So here the faulty circuit is simulated by using one after another. So this is inherently slow. So whereas come to parallel fault simulation. In case of a parallel fault simulation, here the faulty circuits are simulated simultaneously. So this is somewhat advanced when compared to serial fault simulation. Whereas in case of a serial fault simulation, we are going to simulate one after another. Whereas in parallel, we can simulate all the circuits at a time. Okay, it can reduce the time also. So next one is the concurrent fault simulation. Here whole circuit is not simulated, but only a part is simulated where the fault is introduced. Okay, we are going to simulate only the particular part where the fault is there. So it is a very fast simulation when compared to serial and parallel fault simulation. So in this process, many faults are simulated at a time. Okay guys, so now we are going to discuss the last topic. So that is a design for testability. So in case of a design for testability, we have three important approaches. Those are the ad-hoc testing, scan-based approach, self-test and built-in testing. These are the three important approaches in case of a design for testability. So in case of a scan-based approaches, we have serial scan, we have parallel scan, we have boundary scan. Okay, whereas in case of a self-test and built-in testing, we have another classification, that is first one is LFSR, that means linear feedback shift register. It is also called the pseudo random sequence generator. Another name for LFSR is pseudo random sequence generator. So next one is the second one is the signature analyzer and third one is the built-in logic block observer. So simply it is called as BILBO. Built-in logic block observer is simply called as BILBO. So these are the three important approaches in case of a design for testability. So let's see one by one. The first one is the ad-hoc testing. So simply remember guys, this ad-hoc testing is one kind of a software testing. So it is one kind of a software testing. Here it is not a structured testing. So it is some kind of a simply it is a random testing. Okay. Here the no documentation is required, no test design, no test case. So in case of a ad-hoc testing, the main limitation of this ad-hoc testing is it is suitable for the small designs only. So if you wanted to test the large design, if you wanted to test the large circuit, you have to partition that large circuit into small parts. So then we have to perform the ad-hoc testing. So it is this particular testing is limited for small designs only. Okay. It is the combination of different simple test strategies that are used to reduce the number of tests. So what are the methods of ad-hoc testing? So here are different methods we are going to follow while we have to do ad-hoc testing. So here if there is a large circuit, so we have to partition that or we have to divide into smaller ones. Then we can simply do the ad-hoc testing on that particular smaller circuits. Okay. Here the extra test points are added while testing. Here the multiplexers are added to multiplex the scan input and data input. Scan input and data input. So here every state resets are provided. It is not suitable for automation. So it is all about ad-hoc testing. Simply remember ad-hoc testing means software testing. So okay. So next kind of approach is the scan test. So in case of a scan test, always remember this scan test is mainly useful for the sequential circuits. We had already known sequential circuits having some sort of memory. Okay. Here the flip-flops are replaced with the scan flip-flops. So here these flip-flops, all flip-flops are replaced with the scan flip-flops. So let's see what is meant by scan flip-flop. A scan flip-flop has generally two modes of operation. The first one is the normal mode. Normal mode means here the flip-flop will be operated in the conventional mode. That means here flip-flop will operate in the normal mode only. So where in case of a scan mode. So it is somewhat special. So here in case of a scan mode, all flip-flops are connected serially to form a large chain of shift register throughout the IC. IC means integrated circuit. So see here are all the flip-flops. So in the circuit, all flip-flops are replaced with the scan flip-flop. So it is not done by manually. So it is done automatically. Here the test compiler will automatically replaces the flip-flops with the scan flip-flop. This mechanism will be simply called as scan chain insertion. So this particular mechanism we can call it as scan chain insertion. So it is done automatically. So by applying clock pulses, large stream of data can be shifted in and out throughout the chain. Then in this way every sequential circuit is going to verify. Okay, so let's consider the scan flip-flop. This particular scan flip-flop will going to have the two operation modes, that is normal mode and the scan mode. No, so it is the scan flip-flop. So here we are going to use a 2:1 multiplexer and another small flip-flop here. Here if you select for logic 1, so this SI data, so the scan input will enter into this particular flip-flop input D. After that it will going to transfer to the output of the flip-flop, that is the Q. So after that again we have this type of circuit 1 0. Again we are going to have the flip-flop here. Again this Q data will be transferred to this particular multiplexer. Okay, in this way this scan flip-flop will going to work. So for in case of a logic 0, so this data input will initially goes to the input of the flip-flop. Again it will goes to the output of this particular scan flip-flop. In this way this scan flip-flop will going to work. So after that serial scan test. Initially I had said now the scan test have different, again another classification, serial, parallel and boundary. So the first one is the serial scan test. Here in case of a serial scan test also we have two modes, scan mode and normal mode. So in case of a scan mode, so see here this scan-in data will flows through this bunch of registers or a chain of registers which are represented by the dotted lines. So here represented by the dotted lines. So the scan-in input flows through these registers. Whereas in case of a normal mode, so this normal input will flow through the register and the bunch of combinational logics which are represented by the solid lines or the thick lines. So all these are the solid lines. The most popular serial scan test is the level sensitive scan design, LSST. So let's see what is that. So LSST, level sensitive scan design, reconfigurable D flip-flop. So here we have the two kinds of the latches. The first one is considered as the master latch. So the another one will be considered as the slave latch. So okay, here in case of it is also operated in two modes. First one is the scan mode, another one is the normal mode. It is some kind of a special mode. So in scan mode, so D2 acts as a scan in. So S0 acts like a scan out. Here the clock 1 is low. That means the clock 2 and clock 3. Totally we have 3 clocks. Clock 1, clock 2 and clock 3. In case of a scan mode, only clock 1 is low only. Another clock 2 and clock 3 are high in case of a scan mode. So normal mode, just opposite. Clock 2 and clock 3 are low here. Clock 1 is high here. Here the D1 acts like a input. So D1 is the input and Q is the output in case of a normal mode. Simple. Okay. So next one is the parallel scan. Parallel scan already I had said. Scan test is divided into 3 types. So serial, so parallel and the boundary. The second one is the parallel scan. Here the whole chain is divided into smaller scan blocks and each block is scanned independently. Okay. Okay. So the next one is the boundary scan test. So it is useful for the board testing. So in case in order to test the boards, we are going to use the boundary scan test. So it tests the chips present in the board. So mainly we are having the 4 signals. Here the 4 signals are connected to the tap controller. Tap means test access port controller. Here mainly we are having the 4 signals which are directly connected to the tap controller. Tap means test access port. The 4 signals are the test data input, test data output, so test mode select and the test clock. So TDI, TDO, TMS and T clock. So test data input will send the input, test data output will checks the data at the output, whereas test mode select will go into. So here the operation is selected by this particular pin. The operation is selected by using this pin, test class. Here the data is shifted by using this particular pin. We are going to shift the data. Okay. So the next one is the boundary scan register. So here in case of a boundary scan testing, we are going to add the boundary scan register, that is BSR. So the boundary scan register is added to every IO pad in the IC. So these registers are connected in series to form a long chain of shift registers are called the boundary scan shift register. So we are simply your boundary scan register is going to add to every IO pad in the IC. Here the optional control signal, that is the test reset. So optional control signal, that is the test reset, is used. So it is used to reset this particular test access port controller. So let's see the let's see the boundary scan shift register block diagram. So it is the boundary scan test architecture. So all these are the boundary scan registers. So all these are the different types of the tap controllers. We have 4 control signals. I have test mode, select, test clock, and the TDI. So all these are the signals. So it is the architecture of boundary scan test architecture. So all these are the boundary scan registers. Okay. So next one is the built-in self-test. So I had already discussed the design for testability. We have 3 important approaches: ad-hoc testing, scan test, and built-in self-test. So the last one is the built-in self-test. Here the extra logic circuit is incorporated. So why? Because here the extra incorporated circuit will increase the chip size, but it will reduce the test cycle time. The components of BIST module. The components of BIST module I had initially discussed. Various components of BIST built-in self-test are the pseudo random sequence generator. It is also called the linear feedback shift register, simply called LFSR. So next one is the signature analyzer, and third one is the built-in logic block observer. It is simply called as BIL/BO. These are the various components involved in the built-in self-test. So let's see one by one. First one, LFSR, linear feedback shift register. So in case of a linear feedback shift register, it is used to generate the pseudo random test vector. So I had already discussed what is the test vector. So okay, test vector simply it is the input combination. Okay. It is simply used to generate the pseudo random test vectors. Here the outputs at each stage of an LFSR are used as the inputs of the circuit. Okay, so it is a let's consider the 3-bit linear feedback shift register. It is a 3-bit LFSR. Here we are having the 3 flip flops and it is an XOR gate. So it is the architecture of the 3-bit linear feedback shift register. So let's see the truth table. So it is the truth table. So these are the different states of the LFSR. So these are the different types of the clock pulses we are going to apply. So initially, so this particular LFSR will be, so initially the all states are going to logic 1 only. So all states are 1 1 1. So it is the initial state. So it is the initial state. So observe here. So let's see the equations for Q1, Q2 and Q0. So let's see circuit diagram. So observe here this particular Q1. So this particular Q1 and Q2 will act like input for this XOR gate. That means this Q0. That means this Q0 will be the output. No, Q0 output is this particular Q1 with XOR with Q2. Okay, which Q1 and Q2 will be inputs for this XOR gate. Okay, so that means see here this Q0 will equal to Q1. That means Q0 here the Q0 equal to Q1. So here the Q1 equal to Q. Simply remember these equations. So see here in this way we can apply the truth table. So initially all the states in the logic 1 only. Fine. So after that if you wanted to apply the Q0, so what equation we are going to consider? Q0 equal to Q1 XOR Q2. Okay. After that, so see here Q0 means, so it is the initial stage. First one Q0 means Q1 XOR Q2. That means 1 XOR 1 0. After that this Q0 value will transfer to Q1. Q1 value will transfer to Q2. Okay. So and another in same manner. So after the third clock pulse is applied, we have to perform the XOR operation between Q1 and Q2. So that means 1 XOR 1, that is 0. So this 0 will transfer to this side. So the Q1 data will transfer to Q2. Okay. So again we have to perform the XOR operation between the 0 and the 1. 0 XOR 1. So it is simply, so for same inputs we can get the 0. For different outputs, for different inputs you can get the 1. So it is the XOR gate. So it is XOR operation. So here 0 1 0 XOR with 1, that is 1. So after that this 0 transferred to this side, this 0 will transfer to this. In this way you can obtain the states of this particular LFSR. So let's see the signature analyzer. Signature analyzer is simply the combination of an LFSR along with an XOR gate. Simply at the input side, if you connect one simple XOR gate along with the LFSR, it is called as signature analyzer. Okay. So you see here, so it is up to this part we can consider as a LFSR. So if you add the input side, if you add this on XOR gate, so it is called the signature analyzer. So it is formed by adding an extra XOR gate at the input of an LFSR. Here the binary input sequence is applied at the icon. So at the end of the input sequence, the shift register output will form some kind of a pattern. So that pattern will call it as a signature. Okay. So here the test input sequence is applied at the input and the resulted output is compared with the signature in order to determine the fault circuit. Simply remember that signature analyzer means LFSR along with the XOR gate at the input side. So signature means, so here the binary input sequence is applied at the IN. At the end of the input sequence, shift register outputs will form some kind of a pattern. That pattern will call it as signature. Okay. So see here, next one is the last one. So it is the last component of the built-in self-test. That is BILBO. That means the built-in logic block observer. So built-in logic block observer is the combination of the LFSR along with signature analyzer. So okay, the combination of LFSR and signature analyzer will going to give the BILBO. That means built-in logic block observer. So it is, see here. So it is the PRSC means pseudo random sequence generator. It's nothing but LFSR only. Okay, LFSR along with signature analyzer will going to give the built-in logic block observer. Okay. So note, one important note is there. Actually, the two types of EDA tools supported by the BIST, that is the built-in self-test. The two types of EDA tools are the logic BIST and the MEM BIST. Whereas logic BIST used to test the core logic, whereas MEM BIST is used for the memory testing. So it is all about the BIST. So these are the different components involved in this BIST. So it is all about totally designed for testability. Okay, thank you.